Hi, dear students. So, we were discussing the topic enthalpies for different types of reactions. And in that, first one we have seen standard enthalpy of combustion. Then, second one we have seen enthalpy of atomization. Now, this is the third one, that is bond enthalpy. Okay. So, you know that chemical reactions, it involves the breaking of chemical bonds and making of chemical bonds. When you consider the reactant side, there is a breaking of chemical bonds. When you consider the product side, there is a making of new chemical bonds, isn't it? So energy is required to break a bond. To break a bond, you need energy, isn't it? And when you make a new chemical bond, energy is released, isn't it? So there is a change in energy occurring there. When you break a bond or when you make a new bond, there is a change in energy happening, isn't it? So there is change in enthalpy also. Okay. Now next is symbol. The symbol used for bond enthalpy is, you can see delta bond, then H with a superscript which indicates that all the substances are in their standard states. So this is the symbol for bond enthalpy. Now I've said that there is a change in energy happening, isn't it? So because of that, there is a change in enthalpy also. So with reference to the change, okay, with reference to the enthalpy changes associated with the chemical bonds, two different terms are used in thermodynamics. Okay, so the enthalpy change associated with chemical bonds, there are two different terms. First one is bond dissociation enthalpy and the second one is mean bond enthalpy. So we'll be discussing these two terms here, that is bond dissociation enthalpy and mean bond enthalpy. Okay, so let us discuss these terms with reference to diatomic molecules and polyatomic molecules. Okay, we'll be discussing these terms with reference to diatomic molecules and polyatomic molecules. So the first one, that is bond dissociation enthalpy, will discuss with reference to a diatomic molecule. Okay, it is bond dissociation enthalpy we'll discuss with reference to a diatomic molecule. Okay, now consider this example. Okay, this process, that is dihydrogen H2. It is 1 mole of dihydrogen. It breaks, that bond is breaking to give two hydrogen atoms, isn't it? Here the bond is one, what you say, that 1 mole of dihydrogen, it is broken to give two hydrogen atoms, and the what is the enthalpy change is given, that is 435.0 kilojoules per mole. So what is happening here? H2 means two hydrogen is present, in between one bond is present. So you can see hydrogen hydrogen, that bond is broken there, isn't it? That bond is broken there and you will get two hydrogen atoms, that is molecules break down to give atoms, isn't it? So the enthalpy change involved in this process is the bond dissociation enthalpy, that is a bond is broken there, a bond is dissociated there, isn't it? So when a bond is broken, the change in enthalpy, that is called the bond dissociation enthalpy. And in this case, okay, okay, in this case, you can see that this bond dissociation enthalpy, it is same as the enthalpy of atomization. For enthalpy of atomization also we have seen the same example. So for diatomic molecules, the bond dissociation enthalpy and the enthalpy of atomization both are same, one at a same. Okay, the values will be same. So the bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. So you can see all the substances are in the gas phase, that is you can see if a gaseous covalent compound is broken to form products in the gas phase, everything is in the gas phase. So here bond dissociation enthalpy means it is a change in enthalpy when 1 mole of a covalent bonds, that is the substance, that is a reactant should be in 1 mole. Okay, so when you break that bond, what is the change in enthalpy, okay, of that gaseous compound? It is a compound, actually molecule you have taken. So what do you say, when that bond is broken, what is the change in enthalpy? That is the bond dissociation enthalpy. And for diatomic molecules, it is one and the same with enthalpy of atomization. Now there are many other examples also. If you consider any diatomic molecule, the enthalpy of atomization and enthalpy of bond enthalpy, both are same. Now you can see other examples of diatomic molecules, that is chlorine CaCl2. You can see two chlorine atoms is formed, that is the bond between two chlorine, it is broken, and the enthalpy change during that is what is called as bond enthalpy. And you can see the reactant and the product both are in the gaseous state, okay, gaseous phase. Now you can see O2, it gives two oxygen atoms. So these are the examples for what is a bond dissociation enthalpy, okay. And these examples are taken from diatomic, and these are all diatomic molecules, okay. So this is all about bond enthalpy, that is bond dissociation enthalpy. Next we'll discuss mean bond enthalpy. So to discuss mean bond enthalpy, we'll consider polyatomic molecules, okay. So we'll take polyatomic molecules to discuss about mean bond enthalpy. Now consider a polyatomic molecule like this methane CH4, okay. And the overall thermochemical equation is given, that is CH4 gives carbon plus 4 hydrogen, that is both are in the atomic forms, isn't it? Carbon is one atom and 4 hydrogen atoms is given, and the enthalpy change is also given. So in methane, you can see this is methane. In methane there are 4 CH bonds, isn't it? One carbon and 4 hydrogens are present, and 4 CH bonds are present. You can see with white in the white color, that is 4 CH bonds are present, and all the CH bonds, they are identical in their bond length and energy, okay. So all the bonds, they are having equal bond length and energy, but to break these individual bonds, the energy required is different, okay. So to break each bond, the energy required is different. See, even though they have same length and same energy, to break each, that is, you can see 4 bonds are there, to break all the 4 bonds, the energy required will be different in the sense there will be a slight difference in the values, that's it. You can see here CH4, that is methane, gives CH3 plus hydrogen. What is happening there is, from CH4, one bond is broken, okay. So when you break one bond, hydrogen is free, one hydrogen atom is released, and other is CH3 is present, isn't it? One hydrogen atom is broken, one bond is broken from there, and the energy used for that is 427 kilojoules per mole. Now second reaction, you can see CH3, okay. From that CH3, one more hydrogen, that is carbon hydrogen bond is broken, okay. Then remaining is CH2, and one more hydrogen you will get. So the energy released, so the energy used is 439 kilojoules per mole. Now you can see the difference, energy used is different, isn't it? First one is 427, second one is 439. The third reaction, if you consider 2, you can see one more carbon hydrogen bond is broken, so CH will be remaining, and one more hydrogen is free, hydrogen atom is released. So the energy used is 452 kilojoules per mole, and the last one remaining CH, that remaining carbon hydrogen bond is broken, and carbon is set free as atom, and hydrogen is also set free, and the energy used is 347 kilojoules per mole. Now you can see, to break each bond, the energy used is different, the change in enthalpy is different, isn't it? So to in what is say, as a whole, how can you write the change in enthalpy, okay? Because when you break each bond, actually there are 4 carbon hydrogen bonds, so when you break each bonds, the change in enthalpy is different. So which value will you write it as a as a change in enthalpy? So if you take each breaking of each carbon hydrogen bond, it is different, isn't it? The enthalpy change is different. So you can see when you write the overall reaction, that is CH4 gives carbon atom plus 4 hydrogen atom, the enthalpy of what is the change in enthalpy is given as 1665 kilojoules per mole, isn't it? That is the overall. That is when you add these values, that is all the four values, if you add, you will get this answer, that is 1665. Now my question is, when you break one bond, that is if you break one bond, that is delta H, that is change in enthalpy for the breaking of one bond, that is carbon hydrogen one bond, which value will you write it as the change in enthalpy? Which value will you use there? Okay, because for breaking of each bond, the values are different. So for one bond, breaking of one bond, as a general, in general, which value will you write, can we use to write? It is like a confusion, isn't it? Because all the four values are different. So delta H for CH bond, that is to break one CH bond, what is the change in enthalpy? How can you write it, that how can we write that value from these? Okay, it is like a confusion. You can't write 427, you can't write 439, it's like different values. So for as a general, to break a carbon hydrogen bond, if someone asks for methane to break one carbon hydrogen what is a bond, what is the change in enthalpy, how much energy is required, how can we give an answer? It's difficult, isn't it? So for that, what you have to do is, you have to use mean bond enthalpy of carbon hydrogen bond, because in general, to write the value or the energy required to break a carbon hydrogen bond, it is what is a different for each carbon hydrogen bonds, isn't it? So what you have to use is, you have to use mean bond enthalpy for that. Okay, so what you'll do is, you have to add all the values, that is 427, 439, 452 and 347, you will get 1665 kilojoules per mole. Okay, then you have to take the mean value or the average value, you know how to take that value, add all the values and divide it by 4. Okay, so 1665 divided by 4, if you do, you will get 416 kilojoules per mole. So as a general, this average value is taken as the energy required to break one carbon hydrogen bond in methane. Okay, because you have seen that to break each bond, energy is different. So we can't give an answer for that question, how much energy is required to break a carbon hydrogen bond in methane. So for that, what you have to do, you have to take the average value, and this value, that is 416 kilojoules per mole, it is taken or it is considered as the energy required to break a carbon hydrogen bond in methane. Okay, and that is for every bond, any bond, if you consider, that energy is used, that is 416 kilojoules per mole is used to break a bond in methane. Okay, so this is how you take mean bond enthalpy in polyatomic molecules. For diatomic molecules, you can just consider bond dissociation enthalpy. Okay, now when you consider gaseous reactions, gas phase reactions, okay, in gas phase reactions, the standard enthalpy of reaction, that is, you can see delta RH, standard enthalpy of reaction, it is related to bond enthalpies of the reactants and bond enthalpies of the products. Okay, that is it is written here, delta RH, it is equal to summation of bond enthalpies of the reactants minus bond enthalpies of products, and this is particularly for gaseous substances, that is reactions in gas phase. Okay, so here the net enthalpy change of a reaction, it is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Okay, so here the enthalpy of the reaction for gaseous substances, it is the amount of energy required to break all the bonds in the reactant molecules, that minus the amount of energy required to break all the bonds in the product, what is a molecules. And this relationship, it is particularly for what is a gaseous reactions, that is both the reactants and products, they should be in their gaseous state. Thank you.